sometimes. All right, let me give you this real quick while I'm thinking about it. This is a little example of a worked out matrix problem. Just one row. All right, so any questions from that quiz? Yeah, everything. All right. Yeah. Okay. All right, so nobody had this problem, but it's pretty representative. Yeah. So if I wanted to transform this into polar coordinates, I just replace, I'm looking for x's and y's, because I know x is r cosine theta, y is r sine theta. Right? Or if I see this, I know that's r squared. Right? So in this case, I don't see this anywhere, but I see a bunch of these. So I just go ahead and x is
r cosine theta, r cosine theta, r sine.
cool. Just replace each piece with what it is. And then I can kind of, what I could do is I can move that over and that over because this is an extra r. So if I wanted to clean this up a little bit, I could subtract that over, add that over. Oops. I can kill an r. Cool. Poor little r dude. And then I get r equals, I can divide by this if I really felt like it. And get r equals this business here. And then to tell you honestly, I can go further. Cosine, so I get 1 over sine is cosecant. Minus, the sines cancel, I get 1 over cosine is secant. Yeah. So as long as you did a little tiny bit of cleanup, on some of them it's just one step and you're done. I'm not going to make you necessarily complete the square like we were doing earlier. But a little bit of cleanup sometimes is a good idea. Yeah?
You do theta equals 2 pi over 3 converted to...
So if I have theta equals something,
5 over 6.
There we go. 5 over 4, yeah.
2 pi over 4. No, 5 pi over 3.
voting is over. It's a lot like, what do we do if I have this? What do I do? It's the same idea though. What do I do exactly? No, I mean, how do I convert this to rectangular? Multiply by r. Why do we multiply by r? Because I'm missing an r here. So I don't have theta somewhere, but I do have, I have theta equals this. So I know that tangent theta is y over x, right? So what am I really missing here? Tangent. So if I take tangent of both sides, tangent theta is y over x. Tangent 3 pi over 4.
Root 2 over 2.
1.
Almost.
Negative.
Negative. Because you're in quadrant 2, x and y different signs. So you end up with y equals negative x. Cool.
So that's what you...
So you should have all ended up with something like maybe root 3 over 3x or
That's not...
something like that.
Yeah, it was like...
I'm telling you, you should have, not what you did. Not a big deal. It's fine. All right. In general, if you can, you solve for r or you solve for y if you can, because that's the idea of function. Something I can actually plug in the calculator. How do you got the negative 1? Tangent of 3 pi over 4. So tangent of 45 is 1, but that's in the second quadrant. Y and x are different signs, negative. Okay. So this guy, real quick. Last time we did an example of this up on the board. This is actually, I thankfully did not create this whole thing. I found a nifty little website that I will not tell you what it is. You can find it yourself. It lets you put in any size matrix and it'll actually tell you the steps to solve it. The unfortunate part about it for you is it's actually created by a computer, so it will very often do the hardest way possible. Meaning it makes fractions on the first step and then it just carries those fractions through. So if you do find that website, be very careful about using it to do your homework for you because that'll be really obvious to me. It's probably not you doing that.
We were just trying that. Yeah, what if we just like fractions?
Yeah.
Oh, if you love fractions, kick ass. I expect to see them when you test them. If I don't, I'll be very suspicious. But anyway, so I wanted to give you something that steps you through this. You can really see it, and it's all colorful so you can see what it's doing. It didn't quite go exactly the way I normally would go. Do you notice the last 0 it gets is that 0 in the top in the middle? And normally I want to zero out. Normally I want to move this way. In my matrix I want to move this way. So I want to get 1, 0. I want to get these zeros first, these zeros second, these zeros last, and that's just to be safe, that I don't lose a 0. What's up? Oh, you need? Okay. So if you weren't here last time and you have not done matrices before, that's bad. Better come see me or something. Yeah, because we went over how to solve these systems of equations using matrices. Okay.
All the tests we're going to do by hand work or?
Oh yeah. And it will probably give you a matrix which comes out really nice. It's not like a ton of steps, but I just want to make sure you can do the steps. All right, any other questions from homework? Or any questions from homework?
No more quizzes? That was the last one, right?
Last quiz?
That was the last announced quiz, yes.
Oh my God! What will you say that? What will you say that?
What's that? Any other questions? Okay. What I really want to do today is finish out chapter 10.
Okay.
We'll preview 11. We'll get out of here a little early. This is my hope. Let's see what happens.
I like your style.
Okay.
Yes, sir.
So, the 10.4 once you introduce an idea of a different way to represent something, so the very first thing we learn, of course, is just the straight up numbers 1, 2, 3, 4. That's amazing. Then we start talking about how to add them, how to subtract them, what that means, and divide them, multiply them. So we've just learned about matrices, which is a whole different way to represent. One thing it could represent would be a system of equations. Now I want to go one step further. I want to start talking about the algebra. Can I add these matrices together? Can I multiply them together? What would it mean if I did it? So for example, if I add a matrix like that, and a matrix like that, wanted to add these things together, what would your gut tell you to do?
Add them.
Okay, good. Be a little bit more specific.
It's like 1 row plus.
Yeah, each component, I can just add it component-wise, right? And really, you could think of this as, this column could represent, normally it represents X's and Y's and things like that, but it could represent, elephants and lions at a zoo or whatever. Of course, -4 lions is kind of freaky. It could represent profit in thousands. So if last year I didn't make anything, and this year we are down 1, what's the total for the last couple of years? 0 plus -1. -1. And so forth. So this will be 1 plus 5 is 6, and so forth. So thank God addition of matrices is very straightforward. subtraction the same way. 3 and 6, 9. Negative 4 and 11, 7. Okay, nothing major. What would A minus B? Yep.
What if they're not the same size matrices?
Beautiful. We're getting there. I love it.
Calm down, calm down.
Yeah, so for A minus B, what you could do is you could write what negative B is, if you wanted to, just to make negative B is 1, negative 5, negative 6, negative 11. And we just figured out what scalar multiplication really is. And what I mean by that is multiplying something by a number. Right, so if I multiply a matrix by a number, I just multiply each piece of it by that number. So negative B is negative 1 times all these. Twice B would be double all of these.
Yeah.
Because the minute I define addition, I can define scalar multiplication. And when I say that word scalar, that means a single digit, multiplying by a single digit. Because matrix multiplication is a whole other thing, which is coming up soon. So A minus B would be 1, negative 3, negative 4, and negative 15. Yeah. Yeah, if I make it negative B, now I just put the A and the minus B together. Or you could just do 0 minus negative 1, 3 minus 6, right? 1 minus 5, negative 4 minus 11, no big deal. Up to you. I got it, some.
To be correct,
Say again?
to be correct, we just like go straight from A to B.
Yeah, you don't have to do this. You don't have to. You can just do 0 minus negative 1. You just got to remember to change that to plus.
Oh, so we have
So what's 3A?
0.
Yeah, 0,
3.
3, 9, negative 12. Okay, cool. So Brianna had a good point. If you add them component by component, but I have two matrices that aren't the same size, so for example, if I'm trying to add 1, 1, 2, negative 3, and I'm trying to add that to 1, 1, 4, 7, negative 6, 2, this is just an undefined operation. I can't do it. Because it's not 0, 0 here. This is sort of like it doesn't even exist. This is like the earth ends, right? So I can't do anything there. This is not even 0, 0 here. It's just not even a spot for anything. So what's this nothingness plus that? I don't know. Shit. So this is really can't be done, or undefined operation, or illegal operation, whatever you want to call it. Does that make sense? I mean, obviously, you can't add a component to another component if that component does not exist.
This is how everything should be. If I don't know how to do it, it's because it's impossible.
But the problem is now you do know how to do that, and it's still impossible. That's fair. So that's easy enough. Multiplying by a number, adding, subtracting matrices, not a big deal. That's a kick-ass awesome thing. So of course, not every operation can be easy. Stay. And I have to tell you, there are so many convoluted explanations as to why this is the way it is. And everything we do in mathematics, at some point in history, they had to decide to do it a certain way. And normally that way was decided upon because it made further operations easier. So we could have defined a lot of things in an entirely different way, but that would have made other things harder to do. You with me? And in fact, there are currently different definitions. There's the XY definition of a plane. There's the R theta definition of a plane. Sometimes this is easier. Sometimes this is easier. So we have both exist. We're like, cool, man, no problem. So when they came to matrix multiplication, they had to choose some method that would make sense further down the road. Because when they came up, I would love to teach a history math course, because you never get that. In the history matrices, they weren't doing it exactly the order that we learned it, of course. They were doing all this weird stuff with matrices, and on the side they said, man, what would it be if I multiplied it? And they had all this more advanced stuff, and they said, well, what would work well with this stuff at the same time? Right, and this is how they developed what it would be. So, here we go. So I have these matrices. This is just another example of that takes a little getting used to. And we're going to do a couple examples, and then I'm going to show you a very simple explanation as to why this is probably a really good way to define this. It's actually based on the main thing we use matrices for, which is systems of equations. So here's how this works. And how big is this matrix, by the way? 2 by 2. 2 rows, 2 columns. And this one is 2 rows, 2 columns. That's going to become very important here in a minute.
4 by 4.
That's good. I like the guess. And then you're just continuing to randomly say something. But what's going to happen here, here's the definition of the first entry here is the first column, the first row times the first column will be this first. And what do I mean by that? Here's how, you just got to do a couple to get this down. 1 times 2 is?
2.
Negative 3 times negative 1 is?
3.
2 plus 3?
5.
5. All right, so let me do it step by step. 2 plus negative 2 times negative 1 is 3 is the first component. So, and in fact, I could reference this spot as A11. First row, first column. So A12 would be first row, second column. And so forth. So if I do the first row by the first column, I get the first row, first column piece. So how do I get this number here?
Second row.
Good. 4 times 2, 8, plus 5 times negative 1, negative 5. Okay. How do I get this one here? It'd be first row, second column. 1 times 6, 6, plus negative 3 times negative 2.
6.
Cool. So every time we do this, just to go back here again, to get this one, I do this and this. 1 times 2, negative 3 times negative 1. 2, 3. Add them, put it here. So to get here, 6, 6. Add them, put it here. Holy shit.
Wait. Repeat that one.
All right, so here, to get this one, it's this and this, right? 8 minus 5. Bam. What's this?
10.
24 minus 10. Cool.
So you can't switch like C times A.
I like it. So I'm already having some people understand that matrix multiplication is not commutative. We'll see that in a minute.
Can you do the top corner again, the 6 plus 6, I think it's that?
Sure. Let me do the whole thing over again. One. All right. So if I want this piece, in fact, let me tell you the whole story here. I don't know if some of you guys realize, in order for this to work, doesn't this have to be the same length as this?
Yeah.
So don't the number of columns here have to match the number of rows there? If it didn't, we have the same problem as earlier. There'd be components without the alternate components, like, what the hell? So these two have to be the same in order for matrix multiplication to work. And then the cool thing is the answer will be this big, 2 by 2. These the same for it to work. This will be how big the answer is. So right now it's kind of, they're both 2 by 2. It's a little bit hidden in there. What the hell's going on? Everything's freaking 2, Jeff, I know. So we'll do one here in a minute. It's not all 2. But just to go through this one more time. When I do this first row, first column, first row, first column, 2 plus 3. I like that. And then 6 plus 6. And then 8 minus 5. And then 24 minus 10. So I get 5, 12, 3, 14. Cool. Obviously, no. There's nothing very obvious about matrix multiplication. So, do the reverse for me. No division. There actually is no matrix division.
Why?
I don't want to. No, is it 4, 5? Or? There is division, but what's division of real numbers? Isn't it multiplication by the inverse, by the reciprocal? So that's really we're not going to go that far here. We'd have to find the inverse matrix and multiply by it in order to accomplish division.
Let's do that.
Let's not. Let's do this. Now, do you guys notice if this is A, B, right? Let me be careful because that means something else. This is A times B, right? I just made it B times A. Normally, for real number systems, just the real number system, it's going to be the same because you got commutativity. You don't have commutativity for every possible system of whatever the hell you want to use. So this is not going to be the same. So what do we get here? 2 plus 24, 26. 2 plus 24, 26. Negative 6 plus 30.
24.
24. Negative 1 minus 8. Negative 9. 3 minus 10. You're just ahead of me, right? Showing off ESP. So again.
Sorry, guys.
Sorry. So really what I'm doing here, let me show you a whole thing. 2 times 1 plus 6 times 4. So do this and this.
Okay.
2 times 1, 6 times 4.
I get how to make for the first one, no problem.
I love it. So then you keep going. 2 times negative 3 plus 6 times 5.
Oh, okay.
Same idea. The idea doesn't change. You take the whole row times the whole column and put the answer in that row and column in the matrix. So here, you would do this, negative 1, what's this, minus 2? Yeah. Minus 8, and then 3, minus 10. Somebody have a sprinkler. Somebody turn on their sprinkler. All right, so then you have 26, negative 9, what was that, 24, negative 7. So the big thing to get out of that is extra practice to figure out what the hell how to do matrix multiplication. But the bigger thing is that is not the same as that. So matrix multiplication is not commutative. So with real numbers, 2 times 4 is 4 times 2. But with matrices, AB is not equal to BA all the time. Okay. Let's do some more examples. Not yet. So let me ask you this. If I have this matrix here, how big is this matrix?
2 by 3.
Try again.
3 by 2.
3 by 2. So how big of a matrix do I have to have here? What's one size? Yeah, it could be 2 by 3. It could be
2 by
2 by whatever. As long as this is a 2, I'm good to go. Because then this would match up with this. You guys see? That's what we saw earlier. So I could make it 2 by 4. Why not? So 1, negative 1, 2, 5, negative 3, 0, 4, 1. Why not? How big will my answer be? So I know I can do it because these match. I can do it. How big will my answer be?
3 by 4.
3 by 4. So I already know the answer is going to be 3 by 4. Okay, so let's see how we do this. All right. So if I take that, if I take this by this, that answer will go in the first spot, right? So you just do this very systematically. Don't do it haphazardly and go, where does that go? Screw that. First column, I can take it all the way through if I want to. First row. So 1 minus 6, negative 5. Now just keep going. If I do this times this, that answer is going to go next. No. It's very cool with what I put down there so far. 1 minus 6, right? Because I'm doing this row, this column. And now I'm going to do this row, that column. negative 1, 0. So negative 1. Now I'm going to do that row, that column. 2, 8, 10. And then finally that row, that column, 5 and 2, 7. So if you're very methodical, you're not going to miss anything. You're not going to be, where the hell does this answer go? Now move to the second row. So all my answers for this will be in the second row. So now, negative 5, minus 12, negative 17, 5 and 0, negative 10, 16, negative 25, and 4. Now I move to the third row. So all my answers are going to be the third row. 0, negative 9, 0, 0, 0, 12, 0, 3. Easy. Easy peasy.
Why didn't we start out with this?
Right? Yeah,
What's that?
this is way easier than what we just did. I don't get how.
Because we won't get quiz on that.
You don't want.
We don't get quizzed on this.
If I was in a class like this, I would desperately want a little packet of easy in the middle of all this hard. I don't want it harder, 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 harder. Final. I'd rather have hard, easy, hard, easy, hard, easy. Thank God. Okay, well, just appreciate it.
Why don't we get quizzed on this one? If we got quizzed on this.
That's me.
Just accept it. What was I going to do? I forgot what I was going to do. So, you know, if I had, could I do this the reverse? No. If this is C, D, could I do DC? Because what's D? 2 by 4. And what's C? 3 by 2. Why exactly can I not do that?
Because 4 doesn't equal 3.
Because 4 does not equal 3. Yeah. There would be some pieces that don't have other pieces to go with. That won't work. Okay, cool. If I multiplied a 4 by 7 times a 7 by 11, how big would my answer be? 4 by 11. So you can you know how big your answer is going to be. That helps you figure out where things are going to go, how big of a matrix you need at the end. How are we doing so far? So here finally, here's what I just remembered. So this would eventually end up with a 4 by 11. I'm allowed to do it because those are the same. So the one reason why they chose to do this, the big reason we do this is to have something like this here. I want to be able to write that as a matrix, right? But I really, truly, what we really want is to make this into a matrix equation. So when we do matrices and we start row reducing, that's really, to tell you the truth, only part of the picture. It's the only part that we need to be able to do it with it. But what I really will do is what would this be as a matrix? It would be 1, 2, negative 1. Now let's stay with me. Now let's just do X, Y, Z. Negative 1, 4, 3, 1, negative, 3, 1, 1. Now here's the cool thing. What's really going on here is this. Okay. Stay with me now. How would you do this? Could I do this times this? How big is this? How big is this? 3 by 3. How big is this? 3 by 1. So I could do that, right? The inner ones match. The answer is going to be a 3 by 1. Right? 3 by 1. So what do I get when I actually do this? This times this, so what do I get? X plus 2y minus z. Right? And then I get minus x minus y plus 4z. Cool. And so, then I'm going to get 3x. And what is that all? Where's that coming from? I mean, what is that really? That's this, right? So what does it really say? This equals 11, this equals 12, this equals 4, which is exactly what this says.
How can we multiply that 3 by 3 by that 3 by 1 and get a 3 by 1?
We do get a 3 by 1. Totally.
3 by 3.
Give me a break. How many entries are there? That's one entry, isn't it? That's one number. I just don't know what X, Y, and Z are, but that would be one number. So I've got 3 rows, 1 column. These are not separate. These are combined. I just can't combine it because it's not like terms. So that is a 3 by 1. Cool. But so the step we skipped that we really didn't need to be able to get here just to row reduce it was from here to here, to really see where that piece comes from, right? And it's still not the entire picture about how do we go from here to somehow bringing this in there. But that's the next piece. That's the inverse matrix piece. Yeah.
That problem represented in matrices would really be a 3 by 4, wouldn't it?
Exactly.
So can you, off the top of your head, come up with, there's gonna be word problems that make me do matrices like this?
There could be, certainly.
What would cause a 3 by 1 matrix? Like, what kind of word problem would cause that? I'm trying to understand.
Well, you
Sorry,
could
that's
say
weird.
something like,
Like that I would multiply another problem by.
well, you could say something like, every chair. This is the first thing that comes to mind. This is the last word problem I looked at that involves matrices. Every chair takes 4 pieces of wood, 10 screws, and 6 hours to build.
Okay.
Right? So that's what that one matrix could represent. And then the big matrix could be several orders for chairs and whatever else. Right?
Okay, yeah, that makes perfect sense.
All right, good. I'm glad. All right. So you certainly can have word problems that lead up to matrices answering them. Any word problem that would lead up to this, and you know that there's a ton of word problems that lead up to this, would obviously lead up to a matrix that you can convert this into a matrix, right? Okay. So matrix multiplication just takes some getting used to. The operations are not difficult at all. And I'm kind of hoping that taking this backwards and seeing that it does just become this system of equations, this side of the equations, that kind of shows you why I want to define matrix multiplication the way we did. Okay?
Another question.
Yep.
When you come up with the answer for the matrices, do you have to solve it like that at the end? Or no?
Say it again, sorry?
Like, if you did that and you came up with another 3 by 3 matrix, I don't know how you say it, but would you have to make the zeros in the corner?
The product.
So what I have here is a matrix times what we call a variable vector, really, but let's call it a matrix. So I have an A matrix that has my X, Y, Z parts, the coefficients, times my variable parts, equals my answers. Right? So that's really how that's represented. So if we knew, and we're not going to learn this, if we knew how to find the inverse of this, I could just multiply both sides by it. And then my answer would just be this product. And taking the product of matrices is pretty simple. You with me? I mean, it just involves additions and multiplications. Right? So that actually would make solving systems of equations even that much easier. So here, take a minute and do this problem. First off, can you do it? Like, could you theoretically do it? Yes. Because what size is this?
2 by
2 by 3? 3 by 2? These match, so I can do it, and the answer is going to be
2 by 2.
2 by 2. Alright, so what do you guys get here? 4 plus 14 plus 24?
42.
42. That's the answer to everything. So this is 1 plus 4 minus 4.
1.
I like it. Really went on a limb there. 24 plus 35 plus 0. 59. And then 6 plus 10 plus 0. 16. Okay, cool. Now, let me show you this. This might help. But personally, this kind of problem is only really useful to look at. It might help, I guess, but Excel, for example, uses matrix algebra to do a lot of things. Computer programming is simplified by using matrices and arrays of matrices. That's what helps with computer programming. The matrices just do so much more than that. So kind of focusing on that to me is not really giving them justice. But this at least is a good example of a real life problem. This is number 45 on page 670. Hamburger, hot dog, milkshake. So this is the number of hamburgers, hot dogs, and milkshakes sold at these various beaches, Santa Monica, Long Beach, and Anaheim. These various locations, I guess. All right, so this is matrix A. And then we come in with, now of course, if I run this operation in these various cities, I am mostly concerned with the amount of money I'm raking in each place, right? So I need some matrix that actually represents the price per for each product. So if I make my B matrix, this will be hamburgers, hot dogs, and milkshakes, 90 cents per hamburger, 80 cents per hot dog, and $1.10. $1, that's right. So which way could I multiply these? Could I do A, B, or BA? How big is A? 3 by 3, and B is 1 by 3. So I could not do A, B, because then those wouldn't match, but I could do B times A. We're not going to, because I don't want to. We could do it. But what would the answers be? If I did B times A, I would do this times this, this times this, this times this, and add them up. So that's the total that Santa Monica made, right? So yeah, the answer, so if I do 1 by 3 times 3 by 3, my answer will, these are the same, I can do it, my answer will be 1 by 3. Right, so each entry in that row would be how much Santa Monica made total, how much Long Beach made total, how much Anaheim made total. Right? So obviously Excel loves that kind of stuff. It's built on matrix operations. Right? When you ask it to do something for you, it'll use matrix algebra to solve, because it's easy to program that kind of thing. It's just so repetitive, just a loop. Enter the loop until you're done and then exit the loop. That's what matrices really are. Okay. So hopefully that helped. Might have just made people hungry. I don't know. Okay. But if you're curious, and if you're going all the way to linear algebra possibly, you might want to take a look at 10.5. Just to get a little preview.
Is that the bonus?
Yeah, it's part of the bonus. Yeah, so if you're going to go to linear, if you're going to go very much further than this class, you probably should go ahead and do quite a few of the extra credit sections, just to be ready. Yeah.
So the sections that are extra credit, are they going to be on test?
Only as a bonus in that case. Yeah.
How you fixed it on the...
So the green one is the bonus, or is it
The green one have been changed. The ones that have been crossed through are extra credit. So I was just going to throw them out, and I figured, what the hell, I can make them extra credit. Somebody has time and desire.
Have you fixed it on website?
Have I fixed what? I did some of the chapter 10, but not the rest. Oh, I do have to I haven't put any extra credit up there yet because we haven't really gotten there yet until just now. So I'm just going to do section 10.7 and a little preview of chapter 11. And we'll head out.
What about 10?
Huh?
What about
10.8, I'm glad you said that. 10.8 will have to become a part of the extra credit possibilities. Okay. 10.8 is a section that we could live without at the moment. If you do go further and you hit that section, you hit something where you need it, they're going to explain it to you from the beginning. It's not that big of a step from solving systems of equations. 10.7 though is just really useful. I want to get through 10.7. So somebody help me out. Do that.
You gotta make a common denominator.
That's right. Do it.
Right.
Don't say it.
Do it.
Do it.
Multiply over.
Yeah.
Oh my God, somebody's louder than me.
That's amazing.
Yeah. They're telling me this stuff.
Yeah, so this is not that big of a deal. Be careful. It's got to still be a fraction at the end. So I get 2x plus 8. Somebody see where I got that?
Yeah.
This guy's missing an x plus 4. Plus this guy's missing an x minus 1.
All over.
All over this mess here. It can't suddenly not be a fraction anymore. I can't lose that denominator. Unless it was in an equation, then you're allowed to multiply and lose it. So then you get 5x plus 5 over this mess here. So the whole idea of this section is going backwards. Starting here and figuring out, and that's why it's called partial, very often it's called decomposition of fractions, right? Because you're finding out what the components were that went into making this. So how in the hell are we going to do that? Well, here's how we do it.
So why is this a matrix?
You'll find out. When you get more complicated stuff going on, you end up with, and here's the main thing. If I start with 5x plus 5 over this, I can write down where it must have come from. I know it must have come from something over x plus 4 and something over x minus 1. And the thing is, I don't know what that is, so I've got to introduce some kind of variable. So we normally use capital A, capital B, so forth. So the more complicated the equation, the A, B, C, D, E, F, G, who knows, and then I end up with all these equations with A, B, C, D, which might require matrices to solve. That's the idea. Here, this is a very simple one, but I want to show you a couple ways to do this. Are we so far so good? Do you guys see this? If I have something this simple, which I won't always have, I know this must have come from something over x plus 4 plus something over x minus 1. Even forgetting that we started that way anyway, right? So if I just had this to begin with, I can write that down automatically. Maybe. All right.
Maybe.
So real quick on this side, before we keep on with this, if I had, watch out. Okay. What do I have to do first there? Factor. Okay, so I get 11x minus 10 over
Minus 1.
two negatives make plus and minus there, right?
Yeah.
So then this had to come from where? It had to come from A over x minus 4 plus B over x minus 2. That's the whole idea. I'm just trying to break that back up. This is a simple example because the bottom had two linear factors. It gets harder when I have something that I can't factor, or there's repeated factors or something, then I have to get a little more complicated. But let's see how to solve this, and then we'll do that one next. This one I know is going to have nice answers because I made it that way. That one I have no idea. If I had to guess, I'd say it's not going to be nice. The first step on this is I multiply both sides by the LCD. And in a way, that should make sense. I now have an equation I can work with, right? So I now can kill the bottoms. So I get 5x plus 5. What happens here when I multiply by this? Cool. And really, to tell you honestly, I don't do that. I just know from the beginning he's going to pick up the other dude, and that one's going to pick up the other dude, right? So A is going to pick up the x minus 1. And B is going to pick up the x plus whatever that's trying to be. Okay, so there's two main ways to do this. I'm going to show you the way the book shows you first, and then I'll show you the nifty other way. Yeah, it's not the Waller method. It's just the way I was taught a million years ago. So what I do, the book way, is to go ahead and distribute this stuff. Let me just stop right there. You guys okay with that? There's ax plus bx minus a plus 4b. I just want to get my x stuff together and my constant stuff together, right? These will be constants eventually. So can anybody tell me what a plus b must be? Must be 5. Because those are the only coefficients of x I have. In order for this side to equal that side, and this is what we call equating coefficients. A plus b must be 5 because that's what I have there. So you can even take this one more step if you wanted to. A plus bx. So then that must be 5 because that's what I have on that side in front of the x. What else must be true? Yeah, 4b minus a must be 5 because that's the number. These are the numbers, and that's the number I have. So that's the equating coefficients method. This is the one that could lead to a lot of giant matrices if I had a, b, c, d, e, f, g, which very often we do. But this is not too bad, right? I could actually do elimination, couldn't I? Yeah. If I add these directly, a minus a goes away. B and 4b is 5. Is it very cool that you guys see this? And this is now a system of equations. I can use elimination, substitution. I can make a little matrix if I want to. For a 2 by 2, dear God, no need for that. Right? So 5b, a's go away, equals 10. So b must be 2. Therefore, a must be
A plus 3.
Must be 3 plus 2 equals 5. Must be 3. And of course, that's exactly what we had in the beginning, right? A goes on top of x plus 4. B goes on top of x minus 1. And that's what we had in the beginning, right? So you guys try to do that one over there. The one that I already said was probably going to be ugly.
Waller method.
Oh, the Waller method, yeah. So at this point right here, this becomes really useful. That's not that hard, but this method becomes really useful when you have like A through J or whatever. When I really don't want to look at that system of equations, dear God. So right here, when you get to this point, what is x? What is x in general? It's any damn thing I want it to be, right?
Right.
So I'm going to make it 1 for a minute. Why would I do that? Because then that piece goes away, and then I have only one unknown. With it. So I'm going to make x 1, and then I'm going to make x negative 4. And again, you can do either way you like. Right? Personally, this way is just so much better, so much more direct. So if x is 1, what do I get on this side? 5 times 1 plus 5?
10.
10 equals, that goes away, right? That's 0 now. Plus 5b. So I get 5b on that side. So b is 2. Kick ass. Less work than that was. And if x is -4, I get -20 plus 5. -15 equals -5a, right? Plus 0. I'm choosing my x so parts of this go away. So then I get -15 over -5 is a, so a is 3. Bam. So you can imagine, all I need is one more variable to make this way difficult. Pretty damn hard, pretty damn long, right? Relatively, especially relative to how short this would be.
Yes.
Maybe.
I like it.
All right. So try to do that one either way you want. I want to warn you, you're probably going to get fractional answers, but so 176, you're no problem with that. One of those are nice. Oh yeah, you're right. 12, not 2. 26. Oh, I'm going to do both of these. You guys can do either. Now, when you get more complicated equations, just to let you know, the Waller way will that method will often go so far, but then you have to take over with matrices. But at least at that point, you've solved some of the A, B, C, D through J stuff. Then your matrix is not crazy big. But sometimes there are situations where I cannot get it all the way down just using one method. Just to let you know. No, it is foolproof. It will make it easier, if not solve it. But I didn't come up. So if I do it the book way, I get here. So then a plus b must be 11. And -2a minus 4b must be -10. So if I divide by -2, I get a plus 2b equals 5. Cool. And if I subtract, I'll get b, -b equals 6. That's not what I expected. Yeah, okay. Freaky. So, oh yeah, that's right. I forgot. B is -6. And what do you get for A? 17. A must be 17. Cool. Now if you do it the other way, right here you'll just make X what? 2. So So make x2, I get 22 minus 10 is 12, equals 0 plus negative 2b divided by negative 2. You get b is negative 6. And then you make x 4. So you get 44 minus 10 is 34 equals 2a plus 0. So you get a is 17. Same things we got just a minute ago. So what is the answer then? You go to here. The answer will be, and I've erased it. Oh, there it is. 17 over x minus 4 plus
6
yeah. X minus 2, I like it. Cool. Yes, ma'am.
How does that side equal 2? I mean, once you do 12?
Do it again, sir.
Oh, never mind. Figure out what is 12. Hold on.
I get that. So it will be all equal to 11x minus 10, right?
Yeah, at the end it's got to come out to be this, that expression there.
Okay.
Cool. So you either do the equating coefficients method, or you do the method where you realize x is a variable, so you can kind of use that fact to your advantage that way.
How do we get a plus 2b what?
Dividing this one by negative 2.
Why?
Because I can. Just always do that if you can, right? Get rid of the negatives is a good thing, and killing some of the, making the number smaller is never a bad thing. It makes it easier then to do the next step. I just had to change the signs, and bam, it kills the a. Yeah.
If x is, did I write it down wrong? I guess I did. I didn't research it.
Okay. All right. So we still have to look at slightly more complicated situations. The first one I want to look at is all right, so do that real quick.
Oh, the other one just needs another x. Oh, we're supposed to be solving it instead.
So I mean, you're right. This shouldn't be that big of a deal. So multiply x by x minus 1. 7x minus 7 plus 5 is 7x minus 2 over x minus 1 squared. So this gives us an idea of what we have to do when I want to break this kind of thing up. I can't just say that this is equal to a over x minus 1 squared. I have to also include the fact that it might have some x minus 1